geometrically in this diagram.
It's everything up or right from that point.
Exactly, right? So all I would do is I would draw a box here, and I would get this entire thing all the way off to infinity. I get everything there. And I can get all linear combinations of these monomials, and that's the set that I get. Now, what happens when I choose the next ideal? What is I2 in this context? That's the new point that I'm adding. So when I add it as a set of generators, what do I get? Yeah, exactly. And I'm getting this new strip. And the same way, the last thing is I would finally get everything here. So these ideals are actually strictly increasing. And that's the way you break it in general, is that I could be far enough out that I'm just adding along the diagonal. So there's actually a special case of Hilbert's basis theorem just in the case of bivariate polynomials, which is if I give you a set of grid points where any grid point implies anything up and to the right is contained in it. If you give me any set, then it's finitely generated. There's some finite lower boundary. It's kind of an obvious statement, but you can think about it as being implied by Hilbert's basis theorem in this special case. And the fact that you can't have a finite bound before you tell me what the set of things is the same reason that the Hilbert basis theorem is sort of fundamentally ineffective in the sense that you can't tell me the bound just based on the ring. So even if I tell you the ring has this number of variables, you can't tell me a finite bound there. So really what we're saying for these method of moments things is that there is an algorithm, but we don't actually know what the n is. So that's the irony of it. Is there a question?
Yeah, could you do the same proof using this univariate polynomials?
Yeah, you could do it univariate, but I think the picture is prettier this way. And this is the case which is called Dickinson's lemma. It's not the one in group theory, but it's something else. So this is the proof for this flight. So it's an ineffective bound. Right? All right, so let's do, yep.
Can we say anything about the complexity of figuring out n given the polynomial family?
I think that's a good question. I mean, so, I think if you were to use like Grosvenor basis types of things, and then you use simple properties of the actual ideal and write down the polynomials, then you could probably prove an upper bound. But I don't know anything about the complexity a priori of trying to find the minimal set, but maybe you could do it through Grosvenor bases. But that's a good question. I've thought about that a little bit. Any other questions about this? Otherwise, we're going to do more algebraic geometry. I always give you guys a warning. You guys can ask more questions and slow me down.
The graph is wrong.
What's the, what do you mean?
The point that you drew last should be like.
Oh. All right, just for that, we're going to do some algebraic geometry. It's not like I had this planned anyways. All right, so the thing that I haven't substantiated so far is I just gave you a more abstract proof for 6 moments suffice. It works more generally, but then again, we said finite moments suffice. So there's actually, it's not clear the first time you see these things that this is actually the heart of the issue. That's why I presented the 6 moments suffice, and that the rest of it is kind of just really messy details. Now there's a reason for that, is because we can actually think about, once we know this finite n, we have some system of polynomial equations, which we've pinned down exactly what the solutions are. The only solutions are the ones that generate exactly the same distribution. So for a mixture of 2 Gaussians, it would be you interchange which one is component 1 and which one's component 2, and those are the only solutions, subject to being in the valid set of parameters. But actually, the same way that we talked about stability properties for systems of linear equations, there are also stability properties of systems of polynomial equations. It's surprising the first time you see it, but we're working with a finite number of variables with finite degree. And that's enough to actually imply that when you're close enough to satisfying the constraints of some system of polynomial equations, that you're actually close to a valid solution to. So this is really about characterizing what are the valid solutions. It's the epsilon equals 0 case. And let me tell you a little bit about why systems of polynomial equations are, in general, somewhat stable. So these, actually, there are like many different ways to derive these things. Sometimes you can think about them, I'm going to do it through something called quantifier elimination. There's also this Polish name that is really hard to write down and pronounce, and that's a big part about why I'm not going to do it that way. So it's called Wojciechowicz. Can anyone have a guess about how many Z's there are in it? No? Now, the Wojciechowicz inequalities are stronger, but they're more specialized, so that's actually, I'm going to do it through quantifier elimination instead. So let me try and give you a bit of quantifier elimination. So quantifier free formula, before we get to what quantifiers are, is just some expression. And in our purposes, it'll always be expressions where the variables take on real values, because these are the underlying parameters that we care about. So a quantifier free formula is any expression consisting of polynomial equations. So you can have things like pi of x1 to xk equals 0. You can have this in there. You can have polynomial inequalities. You can have things like qi, where this is again a polynomial, is non-negative. And you can combine these expressions using any Boolean operations. For example, or, and, implies will be useful ways of defining it. So it's just, instead of, initially when we talked about systems of linear equations, you would only have linear constraints, either linear equality constraints or linear inequality constraints, and you're only allowed to combine them using and. So you think about LPs, it's really, is there a solution which satisfies this inequality and this inequality and this inequality and so on? And now we're generalizing it in two different ways. Both of those are sort of deadly for getting good algorithms for solving these things, which work with large problems. The first one is that instead of it being linear equations and linear inequalities, they're actually polynomial ones, things like x squared at least 0, or x cubed minus y squared equals 0, let's say. And you can also combine any of these things using Boolean operations like or and. And in general, what you look for is what are all of the satisfying assignments, right? So for example, you could do something like the set of all x and y, such that x squared plus y squared equals 1, x is at least 0, or y is at most minus a quarter. And you would get some part of the circle chopped up into different pieces. So it's a very powerful way to define a set of, a set of solutions to some polynomial equations. You can even use things like implications in there. And an even stronger way to do it still is to allow quantifiers. So it's oftentimes called a first order sentence. Let's say over the reals. It's the same as above, but you are allowed quantifiers like for all or there exists. So you can think about if instead I wanted to define a set, I could think about the projection of this instead. Like I can project it onto just the coordinate x, right? Which would be the set of all x's such that there exists a y where x squared plus y squared equals 1 and x equals 0 or y is at most minus 1/4. So this would in general be what's called a first order sentence over the reals. So it's just the way of defining algebraic objects. Now what I'm really working towards is that this method of moments is really a way of, once we have a finite number of moments, we can define what are all the other things that agree with those first n moments, and we know exactly what they're. They're only the true settings of the parameters we're looking for. But actually there's a stronger way to use these types of ideas to actually write a sentence about how stable systems of polynomial inequalities are. So let's do that. So one last theorem in this crash course from algebraic geometry. Who's heard of quantifier elimination? So this is called quantifier elimination. It's a funny result because I'm never sure why it's actually credited to both Tarski and Seidenberg. So Tarski proved this in some tech report that was written in Berkeley. And then he never published it, and Seidenberg published it for him, and sometimes it's called Tarski-Seidenberg. So it's not clear to me what the addition is, but oftentimes I'll see it referred to that way. In any case, it's good to publish other people's tech reports if they're good. So actually the statement is that for every first order sentence over the reals, there is an equivalent quantifier-free formula. So however I define some first-order sentence with there exists and for alls and Boolean ways of combining polynomial equalities and inequalities, there's actually always a way to remove the there exists and the for alls and get back something without them that only uses polynomial inequalities and equalities and Boolean combinations. So it's a very strong sentence, statement, right? Because one way of defining a quantifier-free formula would just be something like x squared plus y squared equals 1. So we just have a circle. But then as soon as I think about projecting it, and removing the y, then instead I'm going to define x is at most 1 or at least -1. So even though if you've defined it using just equalities, when you project you're going to need inequalities, but there's always a way to actually take this quantified formula and turn it into a much larger formula, but still finite size, which has no quantifiers and only has polynomial inequalities and equality defining constraints. So now the magic is going to happen. So what we're going to do is let me write a really helpful set in first order. And this set the fact that we can remove its quantifiers will imply that we actually have stability properties for systems of polynomials. Let me actually do it over here. I think I need a little bit more space. Are there any questions about the definitions?
Would this be algorithm? Would this be algorithm?
There's an algorithm to do this. These types of things, they run in, so Tarski just proved that there's a finite time algorithm. There's a whole history of study on these things. So I think even afterwards, there were still like doubly exponential time algorithms. These are all over finite sized things, so it's okay. And eventually you can do things in singly exponential. That'll take us a little bit too far off track into the algebra. But I think one of the, so there are these results of Basu et al., which give the best known algorithms for quantifier elimination. They're based on various algebraic types of decompositions, one called the cylindrical decomposition. Okay, so let's think about that definition the same way that what we've been doing throughout is we've been defining some abstract problem, some abstract definition like the notion of Noetherian ring, using properties like the basis theorem, and then applying it to the method of moments. So far, we've used these abstract ideas to prove that finite number of moments suffice. Now what I care about is exploring why systems of polynomial equations are somewhat stable. So let's use this abstract idea of quantified formula over polynomial equalities and inequalities, and let's use the idea of quantifier elimination to understand why they're stable. So let's define the following helper set. So it'll just be over two variables, epsilon and delta. One of these will be how close my moments are to the true moments, and the other will be how close that implies I am to the true parameters. So what we really want is that for some choice of epsilon and delta, it's true that for all theta and theta hat, all pairs of parameters, that mr of theta minus mr of theta hat less than or equal to delta for r from 1 to n implies that the parameter distance of these two is at most epsilon. So this is just a sentence explaining, once we know a finite number of moments suffice, we want to know what the relationship is between epsilon and delta. That's our stability property. It's how close do we need the moments to be so that we're implied that we've learned the true parameters within epsilon. So for example, in the case of mixtures of two Gaussians, what would this parameter distance be? It would be that what we would do is we would instead write it as let me just write this out so that we're on the same page and it's concrete. So this is a way to express the fact that the parameter distance between two different mixtures of Gaussians is at most epsilon. Because you have this freedom about whether you pair component 1 to component 1 and component 2 to component 2, or you pair component 1 to component 2 and component 2 to component 1. So all I would do is I would write out this parameter distance as this quantifier-free formula, as either this holds, or this holds. Maybe what I could do is I could square each of these things to get rid of the absolute value, or I could put in plus minus ones. Doesn't really matter. But the point is that this entire sentence now is a first order sentence over the reals. It expresses how stable the system is. And what's important for this is that, what we already know is that when delta equals 0, epsilon equals 0. That when you exactly agree on the first n moments, you have to have, parameter distance 0, because you match as distributions. Now, if we think about applying quantifier elimination, see, this has this quantifier in here, right? That we care about, is there a choice of epsilon and delta, so that any pair of parameters that are delta close in their moments imply that they're epsilon close in their parameters. But the important thing is we can actually get rid of this quantifier. And that'll give us some set on just epsilon and delta without quantifiers that only uses polynomial relations. So that itself will be a stability bound. So if we apply quantifier elimination, then you can think about what this new, what it would really say is that h of epsilon delta has a new name. There's a way to actually write out what these moments are, given the explicit polynomials, and for 1 to n, and then actually do quantifier elimination to figure out what the new description of h epsilon delta is. And that itself can only involve polynomial constraints between epsilon and delta. So let's plot, what epsilon and delta, what this set looks like. We know that the point 0, 0 is in this set. That's the notion of a finite number of moments suffice, that the only way that we could have matched on all of the first n moments is if we exactly agreed in this parameter distance. But we also know that eventually, you could have ors and ands of these, polynomial equations. But eventually, when you're close enough to 0, only one of those constraints dominates. And whatever that constraint is some polynomial constraint. So we know things like, this entire region is in the set. Because if I tell you you're delta epsilon stable, then if you increase epsilon, you're still delta epsilon stable. Because being delta close to the moments implies you're epsilon close to the parameters, but it also implies you're 2 epsilon close in the parameters as well. Making it larger only increases it. So what you're really saying is that this defining boundary right here is itself a polynomial relationship between epsilon and delta. So what you can do is for any delta, you can define epsilon of delta, to be on this curve where you hit. And what we know is that epsilon of delta looks like some sort of, epsilon is equal to c times delta to 1 over s. So it actually tells us that if we want to get some epsilon target accuracy, it suffices to drive delta down to epsilon to the s. And that then in turn implies the stability bound. So if you think about this set, h of epsilon delta, then what you're really saying is that you have this polynomial constraint that defines it right here. Well, it implies that if the moments are at most epsilon to the s, I'm going to ignore this constant right here, then the parameter distance between theta hat is at most epsilon. So that's sort of the magic of systems of polynomial equations, is that once you have some system of polynomial inequalities with Boolean functions, all these things, which works when you set delta to be 0, and actually implies that the parameter distance is 0, then you can actually write it as a quantified formula, project out the quantifiers, and there has to be some description of this without quantifiers and only using polynomials. those polynomials that define the set are explicitly the stability properties of these systems of polynomials. They imply that, when you've driven delta down to be small enough, that you have a polynomial relationship in how far you need to drive it down to how close you get your epsilon to be. So that's it. So are there any questions about this?
We don't have a bound on the degree of the polynomial.
No, nothing about this is effective, right? So n, we don't know the bound. Now, Tarski-Seidenberg is effective, which is nice. So if we had a bound on n, you could turn the crank, and you can actually make these types of things more precise and get quantitative estimates. But the bigger issue is that we're saying the finite number of moments suffice, but we don't know what that finite is. So it's a more general theory than what we applied for this mixture of two Gaussians, but we don't get the answer 6 moments suffice.
Why? How is it different? Why could we get 6 in the other case?
Because we explicitly use the properties of Gaussians.
Okay.
We use their connections to like the heat equation, other sorts of things.
Okay, so you would have to, for other distributions, you would probably need some other trick like that.
Yeah, that's right.
Find K,
yeah, exactly.
N or whatever.
I mean, so it's nice that 6 is the right answer for Gaussians. Now, you could try and prove for these other things that fit into the polynomial family some finite bound, but I also don't know what the right finite bound is for those things.
So,
in fact, there are even more basic things that won't meet those conditions. Like there's the Cauchy distribution, which doesn't even have lines.
Google.
Oh, any.
They're on YouTube. What? 1849. The
So the
title of the
problem is
course.
that you need to think about distribution.
Pardon? Yeah, YouTube. You're welcome.
So I'm seeing that exists
Oh, okay.
because you say if epsilon is belong to epsilon, I can theta 1, theta 2, theta n, such that like so if I calculate it in this way, should be okay.
Any discrete distributions,
Yeah,
finite supportive values.
Yeah.
Maybe then.
And then basically we calculate the distribution
Yeah.
with the calculation.
But see, one of the issues is that if you do it for all distributions,
Yeah.
any, this bound, I mean, it's definitely not effective, but it's also going to tell you that n moments suffice, or n is your domain size. I mean, it has to, because that's the only way. Otherwise, you just don't have enough degrees of freedom, right? So that's true.
It's actually not useful.
I agree. I agree. I mean, so it's exactly this issue, right? That, for Seyfried-Nun's families, like, exponential families, even for real domains, it's true that a finite number will suffice, and then there's sort of like it won't be too many parameters either. Or something, right? But, one of the other issues is that this also doesn't work in high dimensions. See, what we're crucially using in high dimensions was that the projection gave us linear constraints.
We're awake.
And that's what prevented
We are
us from
awake.
having exponential
We are awake.
in,
So early.
in that. But the other sort of funny thing is that for mixtures of K Gaussians, the proof I gave last time works that 4K minus 2 moments suffice for it. And that actually gives you, you could use this tool, for example, to get bounds on how close you need the moments to be to the true, to get close to true parameters. And you get something exponential in K. So to get epsilon accuracy, you need 1 over epsilon to the, CK samples.
So you're saying you can use this for Gaussian and
Yeah, so this actually is effective. And the way to think about why it's effective is because there's actually an algorithm for computing it.
Okay.
So all of the things about their bounds on the bit complexity of the output thing, and about how large the systems can be, all of that stuff translates into really terrible bounds, but bounds that are finite. But the funny thing is that we also have this lower bound for mixtures of K Gaussians,
Yeah.
that there are two different mixtures,
Uh-huh.
which have a different number of components
Uh-huh.
that are exponential in K close.
Oh, okay.
So to a certain extent, that's inevitable
Uh-huh.
from the way that you've defined the problem. Because if your goal is to learn the parameters,
Sure.
then exponential in K is inevitable. But what's still open is, can you learn another mixture of K Gaussians
Uh-huh.
that's close to true distribution,
Sure.
but does not have, so it's called proper learning then, because you don't care about getting the parameters right.
Is it just then density estimation?
Yes, but
Yeah.
proper density estimation.
Okay.
See, improper, what I could do is I could just take a bunch of samples and smooth them.
Yeah, exactly.
But that doesn't work in high dimensions.
I see.
But what's open still in one dimension
So,
is,
proper, you mean the distribution has to be normalized to one?
no, I mean, it has to be a mixture of K Gaussians.
Okay.
So their proper density, so I give you samples from a mixture of K Gaussians.
Yeah.
Now, if you want to learn the parameters, a barrier to being able to do that is if there are two mixtures that do not have close parameters, but are extremely close.
Sure.
That's not a barrier to proper density estimation, because I could output either of those.
Yeah, exactly.
And that question is actually still open.
Yeah.
So the reason that we looked at the parameter learning problem is because constraints of the parameters imply constraints
Mhm.
on the high dimensional thing that you can then solve for.
Yeah.
But the same way that improper density estimation is trivial on the real line, but is really not, we don't know what to do in high dimensions. You could hope that proper density estimation is a path towards that, even in one dimension.
Sure.
And the issue is that we only have things which run in exponential in K time for that problem. So, but the lower bounds are not a barrier to that problem.
Yeah.
So it's funny that some of these things are still open. But, yeah.
So I'm curious, if you just run a YAM algorithm, and then would any local minimum would be
No.
close?
Let me tell you another open question.
Yeah.
Given an infinite number of samples, does EM have any local optimum?
Oh yeah, I'm very curious about that. Do you know how to?
Someone asked me this question 3 years ago, and I said, of course it does. And then I never thought about it again. But then smart people were unable to find the local optimum. So now maybe if there is no local optimum.
Yeah,
It's actually very possible. Because that's also the way that I gave this